We are now recording. Let's get the slideshow set up from the current slide. And before we get started on this, if you have any questions, start getting those ready and together. Let me make these, especially since the projector's trying to wake up again. Did it even? No, it didn't. Well, it is. Let me try it again. Yeah. I guess it didn't beep. Okay. My office hours, 2 changes I know about coming up both of the next 2 Fridays, tomorrow and next Friday. I have treatments both of those Fridays. They say they're going to be about 7-hour treatments. They're going to start at 7:30 in the morning, so it's not good news, okay? I will not be on campus at all tomorrow or next Friday, okay? Either campus. So if you need to see me, catch me Monday through Thursday of next week. Catch me sometime today. All right. That said, when I got home last night, there was a voicemail on our answering machine that I have a doctor's appointment next Tuesday. I'm not supposed to have a doctor's appointment next Tuesday, so I'm going to call this afternoon. It was too late at night to get them to change, and they're not open yet, or just now opening. So as soon as this afternoon when I'm out of class, I'm going to try to call and see if I can get that changed, because Fridays is when I want to have my appointments if possible, and Monday or Wednesday afternoon would be better than any time on Tuesday or Thursday. So I'll see if I can get that changed. But stand by. This is one time you might want to check Blackboard. Blackboard before coming to class. If I cannot get that appointment changed, I can't remember what time the appointment was. It seemed like it was 8:30, so that would be the problem. So, but I'm going to try to get that changed. Mari? Barely seeing that light. Okay. Any questions for anything we've covered so far? Let me also say this. Diamonds here. The tests, several people have been completing those. If you haven't either started the test or completed the test, please do so as soon as possible, because we are moving right along. If he is here. Okay. Oh, good deal. And papers in. Excellent. Okay, another one. Wow. Okay, the flood started. Come on. Okay. Okay. 2 in a day. That's not bad. Okay.
So get 1 bonus point for turning it in November.
What's that?
So get 1 bonus point for turning in now.
Yeah. And yeah.
I'm getting my 1 bonus point.
Okay. Get it in today. You get 2. It's still October. Okay. Okay. All right. I hadn't thought of that. This is probably the last day of, the month we'll be here. No? Yeah, that's right. Tuesday, Thursday. Now, since, the 31st is Monday, you can still get it in Monday. Isn't it the 31st Monday? Yes. Yeah. Okay. So, still a chance for November. You got the weekend. Use it. Okay. All right, so the other thing I was saying, please get your test completed. We're moving right along toward the next quiz, so not going to be too long. So, no questions on anything we've covered so far? Well, where my mark was for today is on page 128, and I thought we had done this one or one like it. Oh, here's Jessica. Those 2, okay. All right. Now, what we were talking about before was basically talking about characteristics of functions. The section we're in is finding the zeros of functions, but with the zeros come other things. For instance, this function, alpha of x equals minus 2x to the 4th minus 2x squared. First thing to look for there, several things. Let's just review all of it. What is one thing you note about this function? When you look at it, what can you tell me about its graph? It's an even function. That's very good because both of the exponents are even. You don't have any odd exponents. Okay, and it's going down and down. Why?
The coefficient's negative.
Okay, number one, the leading exponent is even, so it's going the same direction, and the negative coefficient meaning that direction is down. Very good. Okay, how many, yeah. Actually, possibly 4 intercepts. And what's another name for intercepts? You were talking x-intercepts. Zeros of the function. Okay? Possibly 4. Okay? Don't have to have 4. The maximum you can have is 4. When you look at this graph, what do you notice? Only 3. But can you tell me anything about this one? Okay, here is something we haven't hit yet, so I'm going to suggest it here. Notice at this 0, the function crosses the x-axis. At this 0, it crosses the x-axis. At this 0, it comes down, but then goes up. It touches, you might say kisses the x-axis, but then turns back and goes in the same direction. When you see that happening, you know that's got to be a multiple 0. In fact, its multiplicity has got to be even. These that cross, 1 and only 1 0, that's a multiplicity that's odd. Okay? And we'll look at that a little bit later, but I just want to point it out now. What else do you notice about this? Hint, hint, hint. Okay, how many maximum turning points could this one have? 3, 1 less than the degree, and how many does it have? 3. So sure enough, that fits. Okay? So that's the situation for this one. In this case, the graph of f has 3 turning points, as shown here, because you could have up to 3, and indeed it does. Now, just visualize this. If you were to add a 1 or 7 or something like that to that, what's going to happen to that function? Up, exactly. And if it goes up anywhere, okay, even 0.5 or 0.3 or 0.1, this is no longer a 0 because now the whole function, remember, it's a rigid translation. It goes up, this one's no longer 0. You still have 0 somewhere out here, but you don't have 1 there anymore. Then you would be down to 2 zeros. Now, what if this had a -3 or -1 or -17? Well, 17 wouldn't be too good. Actually, -3 wouldn't be too good. -0.1, we'll put it that way. What's that function doing now? It goes down a little bit, and as it does, this minimum goes down here, which means it crosses there, and still crosses there. Now, let's say it went down 1. So it was a -1. So this goes down to here. These things don't even reach. How many zeros you have then? 9. Okay? So this one function, here it happens to have 3 zeros. Drop it just a little bit, and you get 4 zeros. Raise it a little bit, you get 2 zeros. Drop it even further, you get no zeros. Okay? So you see, all it would take was putting a constant out here. Slightly, or any positive, drops it to 2 zeros. A small negative makes it have 4 zeros. A larger negative has 0 zeros, no zeros. All right, that was more than they asked for, but there's no extra charge. Okay. Now, this example that we just showed, note that because the exponent is greater than 1, the factor of this factor, and let's see. I can't remember if we did this before. Let's go back to here. And if we were analyzing this function, y'all done a good job. You picked out all the key features. But what would be the first thing? Since it's in blue, I think I will, stay in blue. Looks like it's light blue. What's one of the first things you would do to that to help analyze the function? As in finding its zeros. Say again? Okay, set it equal to 0. Perfect. Okay? And then what would you do next? Factor it. And how would you factor that? Negative 2 x squared. Feel like I'm pulling teeth. And what would you have left? X squared. A little louder? No, because you pulled out the minus sign, that makes that a minus. See, the minus sign out front changes the sign of both of those. -1. Are you through factoring? No. What else? And that's equal to 0, by the way. Negative 2x squared. X, okay, I put plus first. X plus 1 times x minus 1. In whichever order. It doesn't matter which order you write it. Okay? Now, you could have done one more thing if you felt like, yeah, we did this last time. We did factor it. Remember? Now, to find the zeros, you set each of those factors equal to 0, right? Negative 2x squared equals 0, or x plus 1 equals 0, or x minus 1 equals 0. What does the first one give you? X equals 0. Okay? Divide out -2, it disappears. And then x times x equals 0. Either x is 0. But because there's two of them, because that exponent is 2, that's what makes this a multiplicity of 2. It has 2, and therefore it turns there and doesn't cross the x-axis. Each of these, this gives you what? When you solve this equation, x equal -1 and x equal +1. Those are those zeros, but those are single zeros. They cross, they don't pause, they don't do anything, they just cross it. This one, because it's a multiple and it's even, it comes down and acts like it's going to cross, turns around, and goes back up. That's why it's a double zero. And that's what would happen if you drop this just a little bit. Sure enough, it would be 2 zeros. Right there, right? Okay, good deal. And that's what they're talking about here. In example 3, note that because the exponent is greater than 1, that factor, -2x squared, yields a repeated 0 at x equals 0, okay? It's x equals 0 and x equals 0. And that's how I did it the first time I did it last Tuesday. Now here's the box, okay, that focuses on that. Repeated zeros. A factor, x minus a, now this one we had x minus 0, so that made her 0. X minus a raised to the kth power. Anytime k is greater than 1, that yields a repeated 0, x equal a, because you set that equal to 0, solve for that, you get x equal a of a multiplicity k. Okay, that's what I was talking about before. This case, the multiplicity is 2. Now, 2 points here. When that k is odd, now they say k has to be greater than 1. Say it's 3, 5, 7, 15, 85, whatever it is. Okay, when it's odd, the graph crosses the x-axis at x equal a. Now, I'll tell you in a minute, I think we'll show you in a minute what. But if that k is even, like here, or 4, or 6, or 12, or 18, or whatever, then the graph touches the x-axis, but does not cross it, and it goes back in the same direction it was coming from before. But it does that at x equal a. So that's what we mean by multiplicity. If one of your factors, or more than one of your factors, has an exponent that is greater than 1, then you have a multiplicity of that exponent. And if that's an even exponent, it doesn't cross. Odd exponent, it does. I think we're going to hit a couple of examples of that. Let's see. Yeah. To graph polynomial functions, use the fact that the polynomial function can change signs only at its zeros. Now, why is that true? What were the 2 features of a polynomial function? Jazz? Smooth and? Say again? Okay, no points. That means it's smooth. Okay? No angles, cusps, things like that. What's the other one? It's also continuous. Smooth and continuous. Okay? So therefore, since it's a smooth continuous function, the only time that function can change signs, the f, the y change signs, is if somewhere in between there you have a zero. So that's only going to happen at the zeros. Now, it will always happen at a zero, because if you have an even multiplicity, it won't change signs there. Okay, between two consecutive zeros, now then you have to line up all your zeros. A polynomial must be either entirely positive or entirely negative. Because if they're the consecutive zeros, it can't have another zero in between. So it's going to stay positive or stay negative, one or the other. Okay? So these are little features that help you when you're graphing. And that's what we love to do, right? Or at least the book does. Okay. That means that when you put the real zeros of a polynomial function in order, good idea, they divide the real number line into intervals on which the function has no sign changes. Okay? Here's what we're talking about. All right? We found the zeros, didn't we? X equals 0, x equals minus 1, x equals 1. Now, if you put those in order, it's x equals minus 1, x equals 0, x equals 1. Put them in there. Minus 1, 0, 1. Those are your three zeros. That's all you got. To the left of minus 1, we know where it's going because we determined that early on. This was a down, down. So we know it's going down there. That's multiplicity of 1, so it's going to cross. So it has to be positive after that. And it's going to be positive until it hits that next zero, which is this one. Okay? It's got to be positive strictly in between those two zeros. Now, because this is a multiplicity of, the zero is a multiplicity of 2, okay, then it's not going to cross. So that means it stays positive. It gets to 0, but then it goes positive again, because it doesn't cross the axis. Then when it reaches, so it stays positive between 0 and 1, between these two zeros, okay? Then what? F1, what kind of zero is that? Yeah, it's a multiplicity of 1, you might say. It doesn't, and it's odd, so it's going to cross there, and it keeps heading south. But that's where we knew it was going to go because of the negative exponent and an even function. So you see, everything fits. Everything fits here. All right. Any questions about that? That's what this statement was saying. It divides the x-axis, the real number line, into intervals, and you know that there's no sign changes outside or in between those intervals. The resulting intervals are called test intervals, in which you can choose a representative x value to determine whether the value of the polynomial function is positive, that means the graph lies above the x-axis, or negative, meaning it lies below. Did we do any test points? No, we used what we knew about end behavior and about multiplicity, whether it crossed or not, and we could tell exactly where those were going to go. But if you don't know that for sure, you're a little in doubt, pick a value, any value in those test intervals, and that'll tell you where the function is there, and between those zeros, it's got to stay on that side of the x-axis. All right. Now, they move on to intermediate value theorem, skipping the two examples that illustrate what they were just talking about. Shame on them. Okay? Let's do them here. That's about the most room we got on anything. Let's do example 4. Okay? We did example 3. Let's do 4. Sketch the graphs of, whoops, let me get out of light blue and go back to black. Okay, sketch the graph of f of x is equal to 3x to the fourth minus 4x cubed. Okay? Now I'm going to draw the graph, or at least my axes. Okay? Hope that'll be sufficient. Hope so. Okay. I'll even put a few tick marks on it. Tick, 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 tick. Tack, tack. Oops. The negatives go in the opposite direction. Okay. Okay, not very evenly spaced, but you can live with it, right? Yes? Okay. Now, you tell me what you see in that function that will help you graph. What would be positive? Oh, the leading coefficient is positive. Good idea. Good sign. What? Going up and up, because this is an even exponent with a positive coefficient. The leading term. I call it a leading term test. The book calls it leading coefficient test. Leading term test. Even exponent, positive coefficient. The end behavior is on the up and up. Okay? It's going up this way somewhere and up that way somewhere. That's what's going to happen for large x's. Somewhere out there, it's always going to go up. Good. What's the next thing you can tell me about this one? It's what? Okay, at maximum it could have 4 zeros. It may not have them, but at maximum it would. And maximum of 3 turning points. May not have them, but that's the maximum it could have. But you got to almost get a few points on here before you can. So what else? How do you know that? What we better do first is your F word. Let's factor first, and then we'll talk about that. So, well, before you do that, you probably need, if you're looking for zeros, you set it equal to 0. Okay, now you factor. And what would you see as the greatest common factor? X cubed times 3x minus 4 equals 0. Okay, you want to revise your multiplicity? What would you go from there? What's the next thing? Either x cubed is equal to 0 or 3x minus 4 is equal to 0. Well, this would be what? X equals 0 with a multiplicity of 3. What does that tell you? Is that graph going to cross the axis there or touch the axis there? Huh? No, because it's an odd multiplicity, it's going to cross. Okay? And that's a x equals 0. The y is going to be 0. That's what we set it as. So right there, we're going to cross. Now, we don't know which way it's crossing yet, but we'll get there. Okay? What's our next thing we're going to do? How about this other 0? What's it? Help me, help me. How would you find that 0? Add 4 to both sides and divide by 3. 3x equal 4. Divide by 3, and that gives you x equal 4/3. Where in the world is 4/3? 1 1/3. So there's your other 0. So whereas we had a maximum of 4 zeros, we wound up with only 2 because this has a multiplicity of 3. Right? All right. So that means there can't be any more zeros out here. So this function, since it's going to be going up, ultimately, it's going to have to be coming down this way here because it's going up, going that way, down here. Now, since that's a multiplicity of 3, this is what I'm going to show you. It doesn't just do a straight cross there like it would if it was a multiplicity of 1, which really isn't a multiplicity. What it does, it comes down probably pretty quickly because x cubed comes down quickly, and then it sort of acts like a cubic. It bends, but it still crosses. That's what happens. It's like a cubic function. It has that little bend to it, but it's kind of come right back up and hit that multiplicity, that 0, and then it's going up and not coming down again. Keeps going, keeps trucking. That's it. Now that's probably not a very pretty picture of it, but that's how it's going to look. Now, those two zeros broke the number line into how many regions? 3. You got one on this side, one in between, and one on that side. Now, if you wanted to check to see if my reasoning was right, you could pick any number to the left of this 0. What would be an easy one? Negative 1. Okay, so let's pick negative 1 and see what happens. Now, the other point, by the way, and I usually always do this. This one's a little silly this way. But the other thing is that you got your two x-intercepts. What might you look for? You got two x-intercepts. Next thing to look for would be your y-intercept. How do you get that? Set x equal 0. Well, guess what happens if you say x equals 0? 0. So we've already got our y-intercept right there. How many y-intercepts can you have? One and only one, because it's a vertical line. The vertical line test says you can only have one. So you could have multiple x-intercepts, but you can only have one y. You may not always have it, but in this case you do. Polynomial functions, you will always have it. But since you found this to be 0, 0, that's both an x-intercept and a y-intercept. So we really didn't need to do that. But I always like to do it anyway when they're more complicated functions than this. So let's choose x equal negative 1. What will this become? Negative 1 to the 4th power is 1. 3 times 1 is 3. Okay? Negative 1 to the 3rd power is negative 1 times negative 4 is positive 4. So 3 plus 4 is 7. So this should be 1, 2, 3, 4, 5, 6, 7. It should be off a little bit. Should be right there. But you see, yeah, going in the right direction. Positive here, it's got to be positive everywhere to the left of 0. Okay? The next interval was between 0 and 1 1/3. What's a good convenient number in between that? 1. So let's plug it in and see what we get. 3 is 3 minus 4 is negative 1. I didn't go far enough down, did I? Okay? Now, I've got the shape right, but I just didn't get quite the dimensions right. This should be down here. So this is coming down here, and maybe going back up, something like that. But at negative 1, at positive 1, it is a negative 1. But basically that's, oh, yeah, we could try one on the outside. What's a good value on the outside of that last 0? 2. Let's try it. Anyone know what 2 to the 4th is? No, 8 is 2 to the 3rd. 16. 3 times 16? Big numbers. 48. Minus, and what is 2 cubed? I just said. 8. 48, and what's 4 times 8? 32. So it's positive 48 minus 32. 16. Okay, I'm not sure. Yeah, I'm way off here because that'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Somewhere way up there. So I've got this going up. That should be going much steeper here. But you see, I've got the general idea. Okay? That's what it looks like, basically. If you look in the book, their picture maybe isn't quite as pretty as mine, but look at that. They got it too. See how steep it's going up there? All right, good deal. And they blow up the zeros there so you can see. This is a single 0 just crossing the x-axis. This is a multiplicity of 3, which means it comes down, hangs around 0, but still crosses. Okay, so So the higher multiplicity, the longer it hangs there. Well, we saw that in our functions, remember? The bigger the exponent, the longer it hangs near 0. Okay. We're used to that. All right. Any questions on that? That was example 4. Okay? Now they had the little steps. Apply the leading term test, I call it. Find the real zeros. We did. Plot a few extra points. We did, but we didn't have to. We drew the graph. We drew it early and then just checked the points. All right. The polynomial function is in standard form. Why didn't they have this on the slide? I don't know. When its terms are in descending order of their powers, right? When the exponents are in descending order, okay? From left to right. That's how we're used to writing. Before applying the leading term test, I like to call it, to a polynomial function, good idea to make sure the polynomial is in standard form. Otherwise, you might pick out the wrong leading term and have it going in wrong directions. So let's do the next one, which uses that hint. Sketch the graph of this one. F of x is equal to negative 2x cubed plus 6x squared. Yeah, they have this in the right order, so what were they talking about? Minus 9/2 x. Any of you ready to throw up your hands and say, I can't do this, I got fractions? Don't. Keep your hands down. Okay, unless you're answering your question, okay, or asking a question. Okay. So sketch the graph. What's the first thing? Let me draw the graph in here, or at least the axes. Vertical axis, horizontal axis. Okay? I'll put a few tick marks in here. Okay. What are some things you note about this function? Okay. Okay, a little louder. Okay. I think you said it right. I just can't hear well. Okay. Both of them? Okay. Why not? What is the degree of this? 3. Odd, meaning they're going in opposite directions. So they both won't be going down. One will be going down. That's the question. Which one? Okay, the one that way, because normally that would be going up, but because of minus sign, it's going down. So yeah, this is going up to the left and down to the right. Okay, good deal. That's our, and you see why. Odd exponent, leading term has odd exponent, meaning it's got to be going in opposite directions. This flips them over. So the negative is going positive and the positive is going negative. Okay, good deal. What next? Pretty exciting stuff, isn't it? Okay. Okay, you might have a maximum of 3 zeros and 2 turning points. We forgot to go back and check that last one. Is that already erased? Yeah, I already erased it. So if you think about it, it only had 2 zeros when it could have had 4, and when it comes down like it did there and do that, that's not really a turning point. It tried to be, but then it went on down anyway. It only has 1 turning point. Exactly. Okay. This one could have how many? 2. May not, but we could have 2. Next. Next step. Factor. Well, set it equal to 0 in factor. Okay. And what does that factor as? Now, I'm going to cheat some. Is that okay? Okay.
No, you can't.
Oh, I've got it. Okay. Now, what's the one thing you might not like about this one? That fractional coefficient. So I want to get that on the outside if possible. Now, this is going to take some thinking, but I think we can do that. So whatever we take out there, let's make sure it's got a half in it. And that may be all that we do. You want that to be the only thing? There's no common factors, numerical factors, except. Okay, well, no, yeah, I would take out negative half. That's a good idea. A negative 1/2. And what else? What other common factor you see? The x, exactly. So let's take out, now this is really stretching it some, take out a negative 1/2 x. Okay? Now, what do you have left? Second? Second? Well, certainly you're going to have an x squared, but you got a coefficient too. And think of it this way. What is it that when you multiply it by negative 1/2, you're going to get a negative 2? What could you put here that when you multiply by negative 1/2 times whatever you put there, you get a negative 2? 4. Good. Yes. Okay. Okay. Do you see why that works? Now, it works for two reasons. Number one, because it works. Negative 1/2 of 4 is negative 2, right? So that gives you the right answer. But what are you doing when you're factoring? You're dividing. And if you divide negative 2 by negative 1/2, that's what you're doing. Go over to the side and do that. Divide negative 2, I can't write. Okay, negative 2 divided by negative 1/2. Number one, what's your answer going to be sign-wise? Positive. When you multiply or divide two negatives, you're going to get a positive. So let's just get rid of that for right now. And then how do we divide fractional form? Multiply by the reciprocal. Exactly. So that's the same as 2 times 2/1. And guess what that is? 4. That's where it came from. But if you don't want to go through all that, just think, what number could that be? Okay? Same thing here. Now, you factored out a minus, and you notice it changed the sign of that term. What's it going to do to this term? Change it. Yeah, make it negative. Change its sign as well. That's what negatives do. They change things, okay? Now, what will that be then? A little louder? Okay, let's see if 3x would work. Negative 1/2 times 3 would be not positive 6. What would you have to have here for negative 1/2 times this would give you 6? 12. Very good. Okay, 12. And you can go up and do the same thing. It's 6 divided by negative 1/2 is 6 times a negative 3. Okay, so that would be, I think, a negative 2. That would be a 12. 12x, factored out the x, okay? And then how about that last one? First, it's sign. Second, plus. Very good. You factored out the 1/2. What do you have left? Just look at it. 9. Okay. And that's equal to 0. You see how that works? You agree with that? All right. Good deal. Are you through factoring? No. So what might this next one factor as? This is why it was a good idea to get that negative out of the way and also get the fraction out of the way. So negative 1/2 x times, how will this factor? Will it? That's the big question. Will that factor? You don't think so? Okay. Too bad. Okay. Yeah. Okay. Now what do you notice? Good thing to notice about this term and that term. They're both, again? Yeah, they're both positive. That's a good thing to notice. And they are perfect squares. So what might we try? Yes, let's try 2x. What sign? Minus 3 times the 2x minus 3. Let's see if that works. First, 2x times 2x. 4x squared, that works. 2x times minus 3 is? Minus 6x. Minus 6x, that goes to minus 12x and plus 9. Yes, it does. Okay? Now, I don't know if this is helpful, but it gets it into a form we've seen before. That'd be minus 1/2 x times 2x minus 3 squared is equal to 0. I don't usually do that, but because the book had mentioned that, what does this tell you? This has a, what is the 0 here? I like it in the previous one. First, what does, let's go back to this, okay? What does that tell you? So each of those equal to 0, right? And you get negative 1/2 x equals 0, or 2x minus 3 is equal to 0, or 2x minus 3 is equal to 0. Guess what? That's redundant, isn't it? Okay? What does that tell you? You have a multiple 0. And what multiplicity? 2. Okay? All right, but let's find out what the zeros are. What's that first one? Multiply both sides of the equation by a negative 2. That goes to 1. You have x equal 0, of course, okay? And what does the next one tell you? Add 3 to both sides. That gives you 2x is equal to 3. Yes, I heard someone say 3/2. Divide by 2, x equals 3/2. And the other one gives you x equals 3/2. So guess what? That's a double 0 at x equals 3/2. Where is 3/2? I know where 0 is. That's that one. And what kind is that? Single multiplicity, meaning it's going cross there, right? Straight across, you know, no lingering, okay? And the next one, where is 3/2? 1.5, right there. What's it going to do there? What's it not going to do there? Cross. It's going to go back in the same direction. So since you know it's got to be going positive up here, it's going to cross positively here and just go straight across. And then it's going to come back up here somewhere and try to cross but not do it, and it's going to go down. That's how it looks. Okay? We were expecting up to how many zeros? 3. We wound up with 2, but this is a double 0. So you could almost count it twice. Okay, but you can't. It's only 1 0. And how many turning points were we expecting to have? 2. And how many we get? 2. Okay, so that part works out really nice. All right. Now, if you weren't sure if I have my graph situated quite right, what could you do? Test points. Exactly. Now, what might you choose as test points? Name them. -1, 1, 2. Now, let's try those. So when x is equal to -1, okay, let's do this here then. This would be -2, and what's -1 cubed? -1 plus 6 times what's -1 squared? 1 minus 9/2 times -1. I can just write that down. So this is going to be positive. That's going to be 2. That's going to be positive plus 6. That's going to be positive plus 9/2, right? So 9/2 is 3.5. So that's 8 plus 3.5. That's 11.5. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. I don't even have it on the scale. It's way steeper than what I did. But not much, a little bit. Okay? How about this at 1? Let's do that one. F of 1 would be, this is really easy. What do you do? -2 plus 6 minus 9/2. Guess what you do? Every polynomial function, when x is 1, every multiple of 1 is 1. So you just write down the coefficients and add them together. Okay? For -1, you write down the coefficients, but you change the signs of the odd ones, but leave the even the same sign. Now that's a little difficult, but that's exactly what you do. This is odd, that's odd, so you change those to plus. This one is even, so you leave it plus. Okay? But this is going to be minus 2 plus 6 is plus 4, minus 3.5, no, 4.5. Whew, I can't add. 4.5, so that's going to be plus 4 minus 4.5. That's going to be a negative 1/2 here. So I'm not far off, but a little bit. I went down a little too far. Okay, and comes back up here and goes down. Okay, how about our negative 2? This one we're actually going to have to work for it. F of negative 2 is equal to negative 2 times what's negative 2 cubed? Negative 8. Okay, plus 6 times what's negative 2 squared? Second? Positive 4. Minus 9/2 times a minus 2. Okay, what's that going to give us? There is something wrong with my picture. Okay. Whoa, howdy here. Those come out positive, and we got negative. I've done something stupid wrong here. Oh, I put in a negative 2. That's a positive 2. Why'd you let me do that? It was your fault, okay? Okay. That's a positive 8. That's a positive, and that's a positive. Okay, now let's do it. Okay, what does that give you? Negative 16 plus 24 minus 9. Okay, because the 2's go out there. Okay, so that's going to be minus 25 plus 24. That's going to be a minus 1. That's where that one should have gone. Oh, I almost had it on that second curve. So that's what it looks like. Sure enough, that's what it's doing. In behavior work, see, when I saw my in behavior wasn't working, I knew I made a mistake. But we got that right. I put in the minus 2 and it should have been a plus 2. Good deal. All right. And if you look in the book, pretty close to what they got. They may not be quite as neat as ours, but they did okay. By the way, both of those had checkpoints. Good idea to go home, go to the library, go to the classroom, do something, and do your checkpoints. All right. Any questions? We call those test intervals we did at the end. Okay? Now, we're going to talk about a very famous theorem in mathematics. It's the intermediate value theorem. We've actually talked around it, but we're actually going to do it now. You may not realize we talked around it. The intermediate value theorem implies that if you have 2 points on a graph, x equal a, what would the y value be? We were just doing it. Y is? Oh, you haven't forgotten that already, have you? What is y always equal to? Alpha of x. And if x equal a, then y would be? Alpha of x or f of a, right? If x equal a, y would be f of a, right? Okay? And if x equal b, y would be f of b. Okay? So it implies that if you have these 2 points, wherever those 2 points are 2 points on a graph of a polynomial function, as long as the f of a and f of b are not the same. They got to be different. One's greater than the other, one's less than the other. Doesn't matter where. Then for any number d in between f of a and f of b, say f of a is up here, f of b is down here. They just can't be the same. So for any number d that's in between f of a and f of b, somewhere in here, there must be a number c on the x-axis between a and b such that alpha c is equal to d. Don't you love letters? They make a lot of sense on it. Let's see what it is. I was waving my arms. They've actually drawn a picture here. What if f of a is, here's a, there's f of a. Here's b, there's f of b. Okay, they drew, there's the f of b is greater than f of a. It just can't be equal to. Now, for any value d that's in between f of a and f of b, there's got to be some point on the x-axis between a and b so that f of c is equal to that value d. Why is that true? No. Yes, you do. What are two features of a polynomial function? Smooth. Now, the smoothness has no bearing here, but continuous. It has to be. If this is f of a here, f of b there, there's got to be some place on the x-axis between a and b where you're going to be c, because it's continuous. There's no jumps. There's no holes. No gaps. It's got to be. This comes from the fact that polynomial functions are always continuous. You've got to have a value. Every value in between f of a and f of b has to be on that graph in between. And if it is, that means there's some value c such that that's true. Because they're continuous functions. Okay? So here's how we state it. Let a and b be any real numbers as long as a is less than b. Okay? Can't be the same. And you don't want a to be greater either. If f is a polynomial function, smooth and continuous, such that f of a is not equal to f of b, if they were, then, don't do that, okay? But if they aren't equal to each other, then somewhere in the interval between a and b, f takes on every value between f of a and f of b. Now, it may take on a few values outside of that, but it's got to take on every value inside. Here's what I'm saying about it could take on some outside. Let's take this here and say this graph was really doing this. Okay? It still takes on every value between f of a and f of b. In fact, it may take them on more than once. I think that only takes them once. But it does some on the outside too. That's okay. But it takes on every value in between. Got to. No matter how many wiggles and squiggles, because they're continuous function, it's going to have every value in between. Now, the intermediate value theorem helps you locate real zeros of a polynomial function this way. If you can find a value, x equals a, in which the polynomial function, say, is positive, and then later you find another value, x equals b, but the polynomial function is negative. The y is negative. Guess what? You got a zero somewhere in between because it's a continuous function. Then you can conclude that the function has at least one. It may have 7 zeros in between there, but at least one real zero between those two values. Because, got to, because of the intermediate value theorem. And it goes the other way too. If f of a is negative, f of b is positive, got to be at least 1 zero in between there. And that's helpful because not all functions come out easy to define answers, okay? For instance, this one. The function f of x is equal to x cubed plus x squared plus 1, okay? Can you factor that? If you can, congratulations. Oh, I can't. Okay, not practical. Okay. In fact, even if that had been a 2-1 in the 1, not practical. But at least you can use quadratic formula. This one can't even use that. Okay, so what you have to do here is just start picking some values. Now, what's a really easy value to pick for that x? 0, I love it, okay? And that gives you, at f of 0, you get how much? 1, okay? That's a positive value there. Now, guess what? Any positive value is still going to be greater than 1, right? Any positive value is going to be even greater, because that's going to be a bigger positive number. It's going to be a bigger positive number. And add 1 to it, it'll be a bigger positive number. So you're not going to get any negatives going that way, right? So let's come this way. What happens if you put a minus 1 in here? That's a minus 1. This is a plus 1, and this is a plus 1. So you're still positive. So that wasn't big enough. Well, how about a negative 2? That'll be a negative 8. Plus 4, plus 1. That'll be plus 5. That'll give you a negative 3. Ding, 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 ding. You had to have a 0 somewhere between minus 2 and minus 1. Got to. Okay? No way around it. Okay? Because x, the alpha of x is negative down here, positive up there. How do we know if you went far enough that way you're going to get a negative number? In behavior. What does that tell you? Going down to the left, up to the right, got to have a 0 somewhere in there. Hint, hint. Any function whose leading term is an odd degree always is going to have at least 1 0. Always. Now the evens you can't tell. The odds, you know you got to have at least 1. You may have a bunch, you got to have at least 1. So it follows from the intermediate value theorem, there must be a real 0 somewhere between minus x equal minus 2 and x equal minus 1. Now, how do you go about finding that? Well, if you hang on and take calculus, you'll find some really easy ways to do it. Without taking calculus, you're going to have to work hard. So I love calculus. It takes some of the work out of it. Okay? But what you're going to have to do, what value might you choose between minus 2 and minus 1? Negative 1.5, exactly. Negative 3/2, however you want to say that. That's negative 1.5, by the way. Plug that into your calculator, see what you get. Anyone got a calculator? Yeah, negative 1 cubed. Negative 1.5 cubed plus 1.5 squared plus 1. What you get?
My calculator was off the whole time I was counting.
This what?
My calculator was turned off the whole time I was
Okay,
counting.
well then turn it on and type it in again, okay? All right. Difficult problems here, okay? I've done that too. Okay. Negative 1.5 cubed plus 1.5 squared plus 1.
Negative 4.6.
Negative 4.6? That doesn't sound right.
Negative 1.5 cubed.
Plus negative 1.5 squared plus 1.
Negative 4.65.
Okay. I think you entered that. Okay. Okay. What you did was minus a 1.5 squared. This should be, okay, wait. I'll show you what it is. Can you go back to that?
Will you go back to what?
To the thing you entered. Okay, right there. Okay. I have to enter it all again. Okay. Now, here's technically what you should do. Open up, yeah, okay. Okay.
Do it with parentheses.
By the way, everybody, when you're doing this, make sure your number that you're cubing or squaring is in parentheses. Negative 1.5 in parentheses cubed. Because what he did was minus 1.5 cubed, which cubes first and then negates.
Negative 0.125.
Ah, that sounds much better. Negative 0.125. Well, this was a negative 1. That's a positive 1 and a negative 3. Negative 0.125. Is that what you said? Okay. That's somewhere right up around there. Okay? So guess what? You're still slightly negative, but you're not nearly as negative as you were at negative 3. You're really close. Okay? That's negative 1/8, by the way. Okay, now, where would you choose next? Something between negative 1.5 and negative 1. Now, I'm looking at this. I think I'll do negative 1.4. Okay, let's see if we can get positive there. So do that. In parentheses, open parentheses, negative 1.4, close parentheses, cubed, plus, open parentheses, negative 1.4, close parentheses, squared, plus 1. Ah, so that's positive, right? So then now you're on the positive side. So now what we need to do is go back something in between negative 1.5 and negative 1.4. What might you choose? Negative 1.45. How about that? Yeah, I mean, you actually want to go even more negative, like negative 1.47 or something like that. Pick something. Be sure you put them in parentheses. Plug, are you using that one or another one? Okay. You just keep doing, narrow down. Get one on the positive, one on the negative, pick something in between. One positive, one negative, get something in between. You know, keep doing until you narrow it down. You're going to get an answer that you guys, you know what? I call this method the method of exhaustion. Actually, I didn't come up with that. Archimedes did on a different thing. But, you know, you just keep doing it. So, okay, that's close enough. I'll take that as an answer. I'm tired of doing this, okay? You know it's something between negative 1.4 and negative 1.5. Let's see what they say in the book. Do they say in the book? They just say you continue doing it, but they don't give you an answer, okay? But you just keep doing it like we did. Now, once you get to calculus, there's much, much easier ways to do it. All right. Example 6, I think that's the next one here, isn't it? Yeah. Last one, too. Use the intermediate value theorem. Let's see if they got it in here. Okay, wait. By continuing this line of reasoning, you can approximate any real zeros of a polynomial function, any desired accuracy, by just finding something whose y values are across the x-axis, one positive, one negative. Pick some x in between those, and then try again. And then if it goes, yeah, keep going in between. So we're going to illustrate that in example 6. Use the intermediate value theorem to approximate the real zero. They only say 1, so we'll just go for 1. Where would you begin? Begin easy. With x equal 0. What is your y? 1, okay? So we know that f of 0 is equal to 1. Everybody see why that's true? Okay. Pick me another x. I don't care. Okay, how about 1? F of 1 is equal to, second, 1 also. That's not going to help too much. So let's do 1. Nah, I think we need to go in the other direction. F of minus 1, what would that give us? Second? Okay. Negative 1 cubed is negative 1 minus a negative 1 squared is 1 plus 1. Yeah, that's going to be negative. That's going to be a minus 1. So we know we're something in between 0 and minus 1. What's a good value to choose? Negative 1/2. Negative 1/2. So let's try f of negative 0.5. And what does that give you? So we're not using that one at all. Plug it in, plug it in. Be sure you put parentheses around it. Negative, open parentheses, negative 0.5, close parentheses, cubed, minus, open parentheses, negative 0.5, close parentheses, squared, plus 1. What does that give you? Anybody? Lazy people? Only one calculator in the room? Ooh, what if I gave you a pop test today? Wouldn't y'all be hurting, huh? Well, maybe we should do it by hand, okay? What does that give you? Thought the black box would speed things up a little. Positive? Okay, that's in between minus 1 and 1, so I'll believe that. But that's still positive. So now we want to do something between these two. So between negative 0.5 and negative 0.1, you pick it. Negative 0. Between 0.5 and 1. How about, yeah, 0.6, is that what you said? Okay, let's try 0.6. Easy enough for you to say. You don't have a calculator. Okay, okay. Get it out, do it. Okay. What do you get? This is almost as exciting as watching water boil, isn't it? Yeah. No problem. Also positive, 0.424. But see, we're getting closer to 0, aren't we? So now let's go between this one and that one, between negative 0.6 and negative 1. Just keep going, okay? We'll pretend that we kept going. All right? And after a while, they get negative 0.7. Okay, negative 0.8. We give you a negative number. Negative 0.7 would be a positive number. So something in between there, you just keep trucking. And it doesn't actually give you an answer, but it's something between negative 0.7 and negative 0.8. All right, that finished this section. Homework exercises, I would do all of 9 through 14, but check the odd answers in the back. Do either 15 or 17, or both. Any of the odds 19 to 29, either 31 or 33, or both. Any of the odds 35 to 49, either 51 or 53, or both. Any of the odds 55 to 63, 65 to 73, 75 to 87, either 89 or 91, or both. Either 93 or 95, or both. And then any of the odds 97 to 103. You pick the ones closest to your major, I would say. We'll wrap this up next time.